Independent samples t-tests. We'll see you there. Okay, folks, let's get into independent groups t-tests, or independent samples t-tests as they're otherwise known. So similar in terms of graphics, right? We start out with this population and we have a sample, right? And we can't possibly measure every person in the population, which is why we pursue a sample. And so when we design these particular schematics, we're going to see here that the population of interest will take a subset of that population of interest and to generate a sample. But then among the group of people in the sample, we can randomly assign them to either an experimental group, such as aerobic exercise, or to a control group, which is the absence of aerobic exercise. And so in this particular case, when you look at a bubble diagram or a schematic such as this, remember, we're always starting out at a population parameter of interest, and it's impossible to evaluate every person in that population. So we take a smaller subset or a sample of that population, and then in the context of this independent groups t-test design, we want to randomly assign the people in that sample to either an aerobic exercise group or to a control group. So when we move forward with the power analysis, right, we can skip through a few steps here because we know we're still in the t-test family, and the statistical test we want to make sure that we choose is the difference between two independent means or groups. So we're going to have a mean and standard deviation for the aerobic exercise group, and we're going to have a mean and a standard deviation for the control group. We want to know, is the means and the standard deviations between the groups different? So different from the one sample test where we have one sample, one mean, one standard deviation compared to a known population parameter. In this case, we're taking a sample and we're randomly assigning them to two possible conditions. Either we're randomly assigning them to aerobic exercise, or we are randomly assigning them to a control group without aerobic exercise. And so you want to make sure that your t-test family remains the t-test, and that the specific statistical test that you choose for your power analysis is the difference between two independent means or groups. We're still going to keep our type of power analysis as a priori two-tailed test, 0.05 and 80%. Everything else stays the same, and you click calculate, and you should see that the total sample you need for this kind of a research study would be 128 people who are randomized evenly, 64 of which to the experimental group or aerobic exercise in this case, and 64 to the control group. Okay, so let's look at another example. Again, I think these examples are helpful to put it into context. So let's say I want to know if exercise lowers resting systolic blood pressure, right? People who exercise, and I want to know if exercise can improve your blood pressure. So I determined from my a priori power analysis that I need 128 participants in this study, right? 64 in each group. And so I'm going to randomly assign people, 64 of which are going to participate in aerobic exercise, and 64 of which are not going to perform aerobic exercise. They're going to be randomly assigned to stay put and to do a seated control session. The dependent variable, or the outcome variable of interest in this case, remains resting systolic blood pressure. And we're going to measure it at the end of a 40-minute session. So whether you sit down in a chair for 40 minutes or if you perform the aerobic exercise for 40 minutes, everybody's getting their blood pressure checked at the end. And we're going to generate means and standard deviations for the people that had the seated control experience versus the people who completed aerobic exercise for 40 minutes, the mean and standard deviation for them. And so that's kind of what we're looking at here. So why is an independent groups or an independent samples t-test the right kind of tool to answer this kind of question? And there's a couple of reasons for that. First, only two levels exist for the independent variable. Remember, independent variables are categorical in nature, and levels really mean options. So in this particular case, you have the independent variable known as treatment. And you can either get the experimental treatment, which is aerobic exercise, or you can get the control treatment, which is the absence of aerobic exercise. The participants also do not mix with each other. They stay separate, and we independently test them separately. And the other thing is that the participants in each of these conditions, in each of these groups, do not belong to the other group. So they stay separate, and we generate means and standard deviations of the groups themselves. The beautiful thing, though, is that the dependent variable of interest, in this case it's systolic blood pressure, this is going to have to be at least ratio or interval level of measurement. And so because you either have to have a blood pressure or you have no blood pressure, that's going to be a ratio level of measurement that is quantified one time. So in this case, a person enters the study. We randomly assign them to aerobic exercise or to control for 40 minutes. They perform, the 40 minutes goes by, they sit down, we take their blood pressure, and we look to see if the means and the standard deviations of those who exercised is different than the mean and the standard deviations of who do not. So when we think about how are we going to generate our hypotheses, again, we have a substantive, statistical, and symbolic hypothesis. So in a substantive hypothesis, we may say that participants who are randomized to the experimental group, aerobic exercise, are expected to have a lower post-exercise systolic blood pressure than people who are randomized to a control group who do not exercise, right? That's what I think. But then statistically, our null hypothesis is that there will be no significant differences in the means between those who experience the experimental group of aerobic exercise and the control group who do not experience aerobic exercise. Of course, we have to generate our alternate hypotheses, which states that there will be a statistically significant difference between the means, and that either the mean of those who exercise will be lower compared to those in the control, or those who get aerobic exercise will have a higher blood pressure compared to control, because we don't know. We're doing a two-tailed test, so we have to be able to generate our alternative hypotheses in that way to represent both scenarios when we're not sure. So then, to make this look appropriate from a symbolic perspective, you can see that the null, HO, shows that the mean for the exercise group is equivalent or not statistically different from the mean of the control. In H1, the first alternative, you can see that the mean for the exercise group's blood pressure will be greater than the mean blood pressure for the control group. Second alternate hypothesis would show that the mean for the exercise group's blood pressure is smaller or less than the mean for the control. So we're making sure that we have everything represented here, so that way when we run the statistics, we know what the definitive answer is. Okay, let's talk a little bit now about basic assumptions. What conditions need to be met for this test to work? And there are 4 basic assumptions that we need to check for with the independent samples t-test. The first is that we will have a normal distribution of the systolic blood pressure dependent variable for both the experimental aerobic exercise participants and the control participants who do not experience it. So we have to run 2 normal distribution bell-shaped histograms, and they have to be normally distributed in both cases. The second thing that we assume is that whatever our dependent variable of interest is, it's going to be a continuous variable along the number line, and will be at least interval or ratio level of measurement. We've already confirmed that systolic blood pressure is a ratio level of measurement, so we meet that assumption. The third thing that we need to do, and what we talked about when we covered basic assumptions, is the variance of systolic blood pressure has to be similar between the experimental exercise group and the seated control group. And the reason for that is, remember, we don't want to have a little variance in the aerobic exercise group's means and standard deviation for systolic blood pressure, and then a ton of variance in systolic blood pressure for the control group. We want those variances to be about the same so we can make a fair comparison. So we have to check for the homogeneity of the variance assumption. And then lastly, we assume that the scores or the data that's collected from the blood pressure values do not mingle and mix with each other. We assume that a systolic blood pressure for somebody that is randomly assigned to the control group is not counted or somehow mixed with the means in the data that's collected for the experimental exercise group. Okay, so once we verify and check our basic assumptions, our comments about systematic and unsystematic variance remain the same. So when you look at a particular t-test, in this particular case, the numerator is still going to represent systematic variance. The denominator is still going to represent unsystematic variance. But before you could just jump right to the t-test, the first thing that we need to think about is because we have two independent groups, we have to combine or pool their variances in order to be able to combine them into one statistical analysis for a t-test. So the first step before jumping right to the t-test is you have to combine the variances generated from both groups. And the way that you do that is with the pooled variance formula. So remember, S squared, variance is in squared units of the metric. This is representing pooled variance, not pooled standard deviation. And the formula to calculate pooled variance is by taking the sample size for the first group, -1 degrees of freedom, multiplied by the first group's variance, plus the sample size for the second group, -1 degree of freedom, times its variance. And so you're combining the variance equations in the numerator. And then in the denominator, you're simply taking the total sample, N1, plus N2, which is the 128 participants, -2. And the reason it's -2 degrees of freedom is because, remember, I have two separate groups. So I have an N-1 in this group and an N-1 in this group. And so that's 2 degrees of freedom. So once I go ahead and perform my quotient by dividing the data for the numerator by the denominator, I'm then going to be able to plug this pooled variance equation into the S squared P functions of this formula. And once again, we'll have separate lecture videos on how to do this in Excel and to verify them with some of the statistical analysis software and do some live demonstrations in class. But you have to do the pooled variance piece of the equation first. You can't just jump to the t-test because it requires pooled variance. So first thing you got to do when you're doing the math, find out what pooled variance is. Once you have pooled variance, you can then perform the t-test as you normally would. So X bar 1 in this particular case is the average, the mean for the first group, let's call it the aerobic exercise group, minus X bar 2, which represents the mean for the control group. And so again, systematic variance, error that is explained, differences between the two means based off of group membership. And that's how we designed it with the experiment. The denominator is calculated by taking the pooled variance divided by the sample size for the first group, plus pooled variance divided by the sample size for the second group, combining them, and then taking the square root of all of that. So we like to isolate things in terms of work that needs to be done for the numerator, then work that needs to be done for the denominator, and then taking the numerator, explained variance, systematic variance, divided by unsystematic, unexplained variance. And so in that particular case, you'd be able to calculate what the t-test is in this particular case. The other thing to think about then is something that's known as the effect size. If you remember from when we talked about the power analysis, we were estimating what the effect size could be hypothetically, but we can actually calculate that with something that's known as a Cohen's d formula. And D stands for the effect size. So in this particular case, you're effectively taking the information from the numerator here, mean 2 minus mean 1. So in this case, you're taking x2 minus x1 divided by the pooled standard deviation. Pay attention to that. Pooled standard deviation. And so what happens a lot of times that I see people do is they'll take, what I'll see people do is they'll take the x bar 1 minus x bar 2 or x bar 2 minus x bar 1. They can get this part done right, but they get the answer actually wrong either on exams or on an assignment because they just take the pooled variance and divide it and plug it in there. And that's not the right thing. The first thing you have to do, this is asking for pooled standard deviation, not pooled variance. So you first have to take the square root of the pooled variance to get it to pooled standard deviation. And that number is what's represented in the effect size calculation. So make sure not to make that error. So when you're calculating this, the next step, of course, is to determine what's the t-table, okay? So in this particular case, again, we're using a two-tailed test, and we're going to keep our column at 0.05 since we're using an alpha level predetermined at p less than 0.05. And then I need to think about Well, what is the total degrees of freedom? So remember, N1 minus 1, N2 minus 1. So it's N1 plus N2, which is 64 plus 64 is 128, minus 2 degrees of freedom. So 128 minus 2 is 126 degrees of freedom. So we're looking down here, and you can see that 126 would have a degrees of freedom value of about 100 here on the t-table. So if we look and move over to the intersection of that row with the 0.05 value, the t critical value, the cut point, where 95% of scores fall above or below that value, is 1.984. Okay, 1.984 in that case. So that is the value of the metric that we're confirming the t that was calculated at this step to that critical value. And if it's larger, once again, it means there's a statistically significant difference between the experimental group and the control group. Okay. If it's smaller on an absolute basis than the critical value, it means it is not statistically different, and we should accept the null hypothesis because there's no difference between the means and the standard deviations of those two groups. Okay. So how might you write this finding up using APA style? You can use something like the following. An independent group's t-test was performed to compare the post-measurement mean resting systolic blood pressure of a group of patients randomized to either an experimental group, exercise, or a control group, no exercise. The resting systolic blood pressure of the exercise group was 109.33, standard deviation of 11.41, N of 64, and this was lower than the control group, mean of 150.23, standard deviation of 17.5, N equals to 64. T of 108.34, and a difference between the experimental group and control group, T observed, T calculated, of 15.66, P smaller than 0.05, two-tailed, statistically different at the 0.05 level. The difference of 40.91 units, in this case millimeters of mercury, indicated a significant effect, and the 95% confidence interval around the difference between the group means was wide. Okay, so that's your APA, your statistical write-up. How you would answer this in terms of a one-sentence answer to your original question is that a 40-minute bout of exercise appears to lower post-measurement systolic blood pressure compared to a seated control condition. And so that's how you would walk through the independent samples t-test. In the next video, we're going to talk a little bit about the paired sample t-test. So we'll see you there.